Hi children, welcome to today's physics class. In the last class we started the topic AC voltage applied to a series LCR circuit. And today we are continuing with the same topic. What is a series LCR circuit? If I have the three basic components in an electrical circuit, that is an inductor with inductance L, a capacitor with capacitance C, and a resistor with resistance R, and if I am connecting these three in series across an AC source, that forms a series LCR circuit. Right. If I have a resistor with resistance R, a capacitor with capacitance C, and an inductor with inductance L, and I am connecting these three in series across an AC source, this forms a series LCR circuit in AC. Okay, this is R, this is C, and this is L. And in this topic we are going to study about the series LCR circuit. We discussed about individual circuits in the previous topics. There we discussed the relation between voltage and current and also the power dissipated across individual circuits. That is, what is the power dissipated across a pure inductor, a capacitor and resistor. And we are doing the same thing in the series LCR circuit also. We have to deduce expression for voltage and current. Then we have to find out the phasor relation between voltage and current flowing through the series LCR circuit, and also what is the power dissipated across the series LCR circuit. Okay. So to get a relation for current, first I am writing expression for the input voltage that we are providing to the series LCR circuit. Let V of t is equal to Vm sin omega t be the value of voltage, AC voltage that we are providing across the series LCR circuit. Next we have to deduce an expression for current flowing through the circuit. In two different ways I can deduce the expression for current flowing through the circuit. And the first way is using the phasor diagram method, and the second method is the analytical method. We will do both. First we will start with the phasor diagram method. Okay. And to get a solution for current or to get an expression for current using phasor diagram method, first I am assuming a solution for current. That is, I am assuming a solution for current as I of t is equal to Im sin omega t plus phi. Okay. First I am assuming a solution for the current flowing through the series LCR circuit, because after studying the three individual circuits, I found that the pattern of a current equation is the same in these three circuits. That is, when we are taking a pure resistive circuit, the expression for current is I of t is equal to Im sin omega t. And in the case of an inductive circuit, it is I of t is equal to Im sin omega t minus pi by 2. In the case of a capacitive circuit, the equation of a current was I of t equal to Im sin omega t plus pi by 2. So in individual circuits, the expression for current is having almost a similar nature. Only the difference in the phase. Right. In the case of a pure resistive circuit, there is no phase term, and in the case of inductive circuit, you can find along with omega t minus pi by 2, and in the case of a capacitive circuit, the phase is plus pi by 2. And also the individual circuits differ from in the magnitude of the maximum value of a current flowing through the circuit. That is, in resistive circuit the value of Im is Vm by R. In inductive circuit it is Vm by XL. In capacitive circuit it is Vm by XC. So only these two factors are changing in the equation of a current in three individual circuits. And the pattern is the same. So with that I am writing a general solution for the equation of a current in the case of a series LCR circuit, and by applying the method of a phasor diagram I am finding what is the value of Im and what is the value of phi, because these two values are changing in individual circuits. Okay. Now before drawing the phasor diagram of a series LCR circuit, We know in a series LCR circuit, the current flowing through each component will be same. Right. Whenever we are connecting the components in series, the current flowing through individual components will be same and the voltage across individual component will be different. So we are representing, let I of t is the current flowing through all the components and the total voltage will be the sum of individual voltages. Okay, I am providing a total voltage of a V across the combination of this LCR circuit, and the total voltage will be the sum of the individual voltages. That is, what is the voltage across the resistor plus the voltage across the capacitor plus voltage across the inductor. The sum of the individual voltages will be the sum of the equal to the total voltage across the series LCR circuit. Okay, and here I wrote the total voltage is equal to VR plus VC plus VL, and I am adopting the phasor diagram method. So this is not simply the total voltage, it is the voltage phasor. Similarly, this VR is the voltage phasor across the resistor, this VC is the voltage phasor across the capacitor, and this VL is the voltage phasor across the inductor. And we know what is a phasor. We defined what is a phasor. Phase is a vector which is capable of rotating in the anti-clockwise manner. So to get the expression for total voltage, I have to take the vector sum of the individual phasors. Okay. So with that concept, I am drawing the phasor diagram of a series LCR circuit. With the previous knowledge of phasor relation between voltage and current in individual circuits, we are drawing the phasor diagram of a series LCR circuit. Okay. So to draw the phasor diagram, I am taking two axes, and first I am drawing the phasor of a current, because the current flowing through each component will be same. Okay, let this be the current phasor of a series LCR circuit. And if this is a phasor, the length of this phasor represent the magnitude of the phasor. So I am saying that this current phasor is having a magnitude of Im. Okay, next I am going to draw the individual voltage phasors in this phasor diagram. If this is the phasor of a current, we know if I am drawing the voltage phasor of a resistive circuit, in a pure resistive circuit, the voltage is in phase with the current. So if I need to draw the voltage phasor in this diagram, I will draw the voltage phasor in this manner. Okay. So this is the voltage phasor across a across the pure resistor. Next I need to draw the capacitor phasor in this phasor diagram. And we know in individual capacitor circuit, the voltage is lagging the current by an angle of pi by 2, or the current is leading. So I will draw the voltage phasor in this manner. So this is the voltage phasor across the capacitor, and when I am drawing the voltage phasor across an inductor, in an inductor the voltage is leading the current by an angle of pi by 2. So this will be the voltage phasor across the inductor. So here you can see the magnitude of the voltage phasor across the inductor is less, because here I am assuming that the value of a capacitance that I am taking to connect in the circuit is greater than the value of inductance. That's why the voltage phasor across the inductor is less than the voltage phasor across the capacitor. And this is to make the problem in a simple way, we are assuming in this manner. Okay, in the opposite way also you can also take the value of L is greater than C. In that condition, this phasor diagram will have more magnitude than VC. Okay, so we drawn the phasor of a current, and we drawn the phasor of individual voltages. Individual voltage phasor also we drawn, and the angle between these two phasors is 90 degree, and the angle between the voltage and the current of VL is also 90 degree. Okay, so next, to get the total, I need to take the vector sum of these three vectors. So how we will take the resultant of 3 vectors? We know the vector addition method. To get the resultant of 3, first we will take 2 vectors, then we will find the resultant, and with the resultant we will add the next vector, and that will be the final value of the resultant vector. So that method we are adopting here to get the total voltage across the series LCR circuit. Okay, if we are getting that expression for total voltage, then only we will get the expression for maximum current flowing through the circuit. Our purpose is we need to get an expression for Im, and also we need to get an expression for phi. Okay, so before finding the resultant of these 3 voltage phases, I am assuming let VCM is the maximum value of voltage across the capacitor, and that I am writing as VCM is equal to Im into C. And similarly, VLM is the maximum voltage across the inductor, that I am writing as Im into L. That I am writing as Im into L. And similarly, let Vrm is the maximum value of voltage across the resistor, that I am representing as Im into R. Okay, so if I drawn the phases here, the length of this voltage phasor represents the magnitude of this phasor. So the magnitude of this phasor is VCM, and the magnitude of this phasor is VLM, and the magnitude of this phasor VR is Vrm. Okay, so next we are going to add these 3 phases, and phasor is a vector, so instead of saying adding phases, we can say we have to add these 3 vectors. So first I am taking these 2 phases and I am taking the vector addition, and with the resultant I am adding this VR. Okay, so now look at these 2 vectors, that is the voltage vector along or voltage phasor along inductor and voltage phasor along capacitor. Both are lying in one line but in opposite direction. That is the angle between the 2 phasors is theta equal to 180 degree. Okay, so when I am adding these 2 vectors, I will get a resultant which is pointing in a direction where the magnitude of the individual vector is more. So you can see in this picture, the magnitude of VC is greater than the magnitude of VL. So when I am adding these 2 vectors, the resultant will be pointing along the direction of VC. Right. So I am redrawing the phasor diagram here. This is the current. The current is greater than individual voltages because the current is the total current and the voltages are the individual voltages. Okay, this is VL. Sorry, I am drawing the resultant here. Okay, so this is VR, this is I, and I am adding these 2 vectors. So I will get a resultant 1. And the resultant will be pointing in a direction where the individual magnitude is more. So this I am representing as VCL. Okay. And this VCL is having a magnitude of VCM minus VLM. And this is VRM. Right. The magnitude of VCL is VCM minus VLM. What is VCL? VCL is the vector sum of VC and VL. When we are adding these 2 vectors, when we are applying the equation of root of a square plus b square plus 2ab cos theta, we will get a root of, instead of a we have to substitute the magnitude of VC, and the magnitude of the phasor VC is VCM. So here VCM square plus VLM square plus 2 VCM VLM cos theta. And if we are substituting theta equal to 180, this will be in the form of VCM square plus VLM square plus 2 VCM VLM, which is in the form VCM minus VLM the whole square. So we will get the magnitude of the resultant VCL as VCM minus VLM. Okay. So now this is the VR vector and this is the VCL vector. And we need an expression for total voltage. Now how to get the total voltage? Again adding the resultant with the remaining vector. So the total voltage V be the vector sum of the resultant plus the individual vector VR. And when we are doing the vector addition of these two, I will get the resultant voltage phase. Okay. Now this is the way how we will find out the resultant of the voltage phasor across the resistor and the resultant VCL. Anyway, I will show you how we are getting the resultant value. Okay, this is our voltage phasor across the resistor VR, and this is our resultant VCL. And we have to find out what is the resultant of these two vectors. We have to do the vector addition, and you learned the triangle of vector addition and parallelogram of vector addition, and you also learned that if the angle between two vectors is 90 degree, the resultant will be lying by making an angle of 45 degree with the x-axis and y-axis. So to get the resultant of VR and VCL, we have to draw the line likewise, because the angle between VR and VCL is 90 degree. That you can clearly see in this picture. This VR is along the line of the current, and with the current this VCL is making an angle of 90 degree. So the same line of current is the voltage phasor across the resistor. So the angle between them will be 90 degree. The angle between this VR and VCL will be 90 degree. So the resultant will be by making an angle of 45 degree with the x-axis and y-axis, that we are labeling with V. Okay, so that you can see from this picture, this is our voltage phasor across the resistor, this is our resultant VCL, and the resultant of these two will be a diagonal which is passing through 45 degree, and that is marked as V. Okay, now our purpose is we have to find out what is the magnitude or what is the maximum value of total current flowing through the circuit. So the magnitude of this line will be the maximum value of voltage, right? The magnitude or the length of the line of the length of the phasor represent the magnitude of that particular parameter. Okay, so as marked in the diagram, this represents the magnitude of this VR is VRM, and the magnitude of this VCL is VCM minus VLM, and the magnitude of the resultant or the total voltage will be VM. We have to find out what is VM, then only we can write an expression for IM. Now to get VM, we are using Pythagoras theorem. To apply Pythagoras theorem, we have to construct a right angled triangle. So from this line, I am drawing a perpendicular, then this will be 90 degree, and this will be the hypotenuse. I am marking this as ABC. It is clear from this diagram. We are taking a right angled triangle ABC, and the angle between, here you can see the angle between the voltage phasor across the resistor is making an angle of omega t plus phi with the horizontal axis. So the angle between VR and resultant will be phi, and the angle between the V and the horizontal axis will be omega t. So the total angle is omega t plus phi. Okay, so we need to get what is the magnitude of our hypotenuse. So we have to apply the Pythagoras theorem. According to Pythagoras theorem, the hypotenuse square is equal to, that is Vm square is equal to opposite side square plus the adjacent side square. Okay, so you can clearly seen from this diagram, the opposite side, that is BC. The side BC is parallel to the phasor VCL. So instead of this BC, we can write VCM minus VL. That you can see from this picture, this side is parallel to this side and the magnitude of this side is VCM minus VL. So the BC will be equal to VCM minus VL. Okay. So opposite adjacent square plus opposite side square, that is VRM square plus VCM minus VLM the whole square. Right. Okay. We need to get what is the maximum value of voltage, total voltage flowing through the circuit. Now we have to do some rearrangement in this equation. We need to get an expression for I. So we have to make this equation where the Im term is coming. To do that, I am taking the voltage expression across a capacitor, resistor and inductor. We already wrote that this VRM is equal to Im into R and VCM is equal to Im into XC and VLM is equal to Im into XL. So from this equation we have to substitute instead of VRM this Im into R, VCM, VLM in this equation. So we will get Vm square is equal to, instead of VRM square I am substituting Im square into R square plus, instead of VCM square, instead of VCM I have Im into XC minus, instead of VLM Im into XL the whole square. So you can see in these two terms Im is common. So I am taking that Im term outside. So I am getting Im square inside the bracket R square plus XC minus XL the whole square. Okay, now I need an expression for Im. So I am taking this Im term to the left. I am forming an equation for Im. So Im square is equal to Vm square whole divided by R square plus XC minus XL the whole square. Okay. So this is Im square. We have to make it into Im. So I am removing the square term. I am getting Im is equal to Vm divided by root of R square plus XC minus XL the whole square. Okay. Now you just compare this equation with the maximum value of a current equation in the individual circuits. When we are taking the case of a pure resistive circuit, Im equal to Vm by R. For a capacitive circuit, it is Vm divided by XC. For an inductive circuit, it is Im is equal to Vm divided by XL. Right. So if we are representing this denominator likewise with any parameter, we can make the maximum value of a current flowing through an LCR circuit in the same pattern as in individual circuits. For that I am taking a term and that term is known as a Z and its value is impedance. This is known as the impedance of an LCR circuit and this is represented as Z is equal to R square plus XC minus XL the whole square. This equation is very important. The impedance of a series LCR circuit, Z is equal to root of R square plus XC minus XL the whole square. Now we can rewrite the equation for maximum current as Im is equal to Vm divided by Z. Okay. So from where we started from this equation. We assumed a solution for current, that is I of t is equal to Im sin omega t plus phi. We assumed a solution for the current flowing through the series LCR circuit, and we need to find out what is the value of Im, what is the value of phi. The value of Im now we found with the help of a Phasor diagram, and its value was Im equal to Vm by Z, where Vm is the maximum value or peak value of voltage, Z is the impedance in the LCR circuit, series LCR circuit, and Z equal to root of R square plus Xc minus XL the whole square. And similar to XL, Xc and R, the unit of impedance Z is also ohm. So this term Z is playing the role of resistance in a series LCR circuit. Right. Now next we have to find out what is the phase of a current in a series LCR circuit. So next to find the value of phi. That is, we found what is the maximum value of a current. Next we need to find out what is the value of phi. Then only we will get a complete expression for the total current flowing through a series LCR circuit. And in this diagram you can see this phi we marked as the angle between the total voltage and the voltage across the resistive circuit. And we know the voltage across the resistive circuit, the phasor of the resistive circuit and the total current is flowing in the is having the same phase, right? You can see in this picture the phasor of voltage and current are in phase. So if we are able to calculate the angle phi between this VR and V, we are actually getting the angle between V and I. Okay, so to calculate the value of phi with the non-parameters, we are considering impedance triangle. Impedance triangle. Okay, I told you what is impedance. Impedance is the total resistance offered by a series LCR circuit, and we are using the letter Z to represent the impedance of a series LCR circuit. So from the impedance triangle, we can calculate what is the value of phi. Okay, so what is an impedance triangle? It is a triangle connecting the value of impedance, the resistance and the reactance. So it's just a triangle. So we are creating this impedance triangle from this right angle triangle that we formed here to calculate the value of Vm or Im. This right triangle ABC. Okay, so from the heading itself you can see this is a triangle where only the resistance terms are coming. So this is the impedance triangle. It's a triangle connecting the impedance, resistance and the reactance. Okay, so from this right angle triangle you can see the hypotenuse is the total voltage flowing through the series LCR circuit. And what is the resistance offered, total resistance offered for a series LCR circuit, that is the impedance Z. So similar to this triangle, the hypotenuse form the total voltage. So here also the hypotenuse form the total resistance. And one side will be the resistance and the other side will be the reactance difference, that is Xc minus LL. Xc minus XL, just like this triangle. And what is angle phi? Phi is the angle between the voltage phasor across resistor and the total voltage. Similarly, in terms of resistance we are taking, phi will be the angle between the total resistance and the resistance across the resistor. Right. Why we are drawing impedance triangle to get the value for phi? Because while starting the derivation, the only three things we assumed are we have three components with inductance L, capacitance C and resistance R. These are the only known things. And one more thing that we know, that is the value of voltage we are providing to the series LCR circuit. So we have to represent this phi in terms of these parameters. That's why we are taking impedance triangle to get the value of phi. Now from this triangle, you can write what is tan phi. What is tan phi? From this triangle, tan phi will be equal to Xc minus XL divided by R. Right. Now the value of phi is in the terms of all the known parameters. Xc we can calculate using the formula 1 by c omega if the value of omega is known. And XL also we can calculate using the formula L omega. The value of R is also known. Okay. So from this expression I can calculate phi. What is phi? Phi is equal to tan inverse Xc minus XL divided by R. Very important relation. Okay. So this phi is the phase or the angle between the voltage and total voltage and the total current flowing through a series LCR circuit. Now our equation is completely solved. From where we started by assuming a solution for the current, total current flowing through a series LCR circuit, and we got that as I of t equal to Im into sin omega t plus phi. The two unknown parameters in the equations are Im and phi. The value of Im is, we found that as Vm divided by Z, where Z is the impedance of the series LCR circuit and which is equal to R square plus Xc minus XL the whole square. Next, we calculated what is the value of phi. Because depending upon the value of phi, the angle between the current and voltage will change. Right. So phi is equal to tan inverse Xc minus XL divided by R. So the magnitude of the capacitance, inductance and resistor will define the value of phi. So from the expression of phi, you can conclude one thing. That is, the phase angle phi between the voltage and current in a series LCR circuit is not a fixed value. In the case of a pure resistive circuit, we found that the value of phi is 0. That is, the voltage and current in a pure resistive circuit is 0. The voltage and current in a pure capacitive circuit is having a phase difference of pi by 2. There the current is leading by an angle of pi by 2, and in an inductive circuit the current is lagging by an angle of minus pi by 2. These are fixed phase angles. But here in the case of a series LCR circuit, the value of phi is not a fixed value, just like this individual resistive, capacitive and inductive circuit. The value of phi will change with respect to the values of Xc, XL and R. That is, with respect to the values of inductor, capacitor and resistance that we are connecting in the series LCR circuit, and also with the angular frequency of the AC source, the value of phi will change. That can be any value. That can be 0, plus pi by 2, minus pi by 2. That can be 30, 60. So we can't generally say that the value of phi in a in a series LCR circuit is not a constant value. Depending upon the values of Xc, XL and R, the value of phi will change. Okay. So while deriving this entire derivation, we assumed one thing, that the Xc is greater than XL. So from this equation of phi, if Xc is greater than XL, you will get this entire term as positive. That is, phi will be positive. Okay. If Xc is greater than XL, phi will be positive. If phi is positive, we can say that the circuit is predominantly capacitive in nature. Okay, in capacitive circuit, we found that the current is leading by an angle of pi by 2. So, if we are getting the value of phi positive, the series LCR circuit is predominantly capacitive in nature. And if XL is greater than Xc, from this expression you can see if XL is greater, this term will be negative. So, we will get the value of phi negative. And when we are getting the value of phi negative in the case of an inductive circuit, so we can say like this: if the value of XL is greater than Xc, the series LCR circuit is predominantly inductive in nature. It will show more inductive circuit nature. Here the LCR circuit will show more capacitive circuit nature. What is mean by more capacitive circuit nature? That is, in a capacitive circuit, the current is leading the voltage by an angle of pi by 2. So we can't say the angle as pi by 2, but we can generally say that if Xc is greater than XL, the phi will be positive, hence we can say that the capacitor is predominantly the circuit is predominantly capacitive in nature and the current will be leading the source voltage. Similarly, if XL is greater than XC, we can say that the phi is negative, that is the circuit is predominantly inductive in nature and the current in the circuit will be lagging the source voltage. Okay. Now, once we derived the expression for current and we found the phase relation between voltage and current, we can represent that using phasor diagram. How to draw the phasor diagram of a series LCR circuit? We drawn the phasor diagram of a pure resistive circuit, capacitive circuit and inductive circuit. How we will draw the phasor diagram for a series LCR circuit? The method is the same. We have to plot the voltage current graph and from the graph we have to select one instant of time and from that we have to draw the phasor diagram at that particular instant. So we can draw the phasor diagram of a series LCR circuit in different situations. For example, in a series LCR circuit that I took to study, in that circuit assume that if X is greater than XL, the nature of a phasor diagram will be similar to the phasor diagram of a pure capacitive circuit. Because when X is greater than XL, we found that the circuit is predominantly capacitive in nature. Therefore, the value of a current will be leading the source voltage. Right. So, if in the question they are saying draw the phasor diagram of a series LCR circuit with XC greater than XL, the graph will be the phasor diagram will be similar to the phasor diagram of a capacitive circuit. Okay, in a capacitive circuit, the current is leading the voltage. Okay, so the current will be starting from maximum and the voltage then is starting from the minimum. This is the voltage curve and this is the current curve. And I need to calculate and I need to draw the phasor diagram at a particular instant. So I am taking an instant of omega t1 here. How the phasor diagram will look like. This will be the current value and this will be the voltage value, and we know in a capacitive circuit the current is leading than the voltage. So this is will be voltage, this will be current, and in an LCR circuit this is not pi by 2 but instead of that a particular angle phi. Okay. Now if in the question they specified draw the phasor diagram of a series LCR circuit with XL greater than XC. When XL is greater than XC, the capacitive the circuit will be predominantly inductive in nature. There the current is lagging the voltage by a particular angle. Okay. So how to draw the phasor diagram of a series LCR circuit with this condition? So this will be the current and this will be the voltage. Okay, this will be the current graph, this will be the voltage graph, and I am taking one particular instant here. I need to find out or I need to draw the phasor diagram at that instant. Okay. Okay, this is the voltage which is leading and this is current which is lagging. So this is current, this is voltage, between them we have a particular angle phi. Okay. So we drawn the phasor diagram with the condition Xc greater than XL and XL greater than Xc. What will happen if in a series LCR circuit the value of Xc is equal to XL? If the value of Xc is equal to XL, the capacitor will behave just like a pure resistive circuit. So the phasor diagram will be look like the phasor diagram of a pure resistive circuit. With X equal to XL, the voltage and current will be in phase. So if we are taking a particular instant omega t1 here, this will be the current and this will be the voltage. Both will be in phase. This will be I, this will be V. Okay. So with these three conditions, the value, the situation, the nature of a series LCR circuit will change. Okay. When X is greater than XL, it will be capacitive in nature, and with this condition it will be inductive in nature. With this condition it will be resistive in nature. Okay.